Okay, hello everyone. Welcome to MCLA and tonight's Green Living Seminar presentation. I'm Elena Traster in the Environmental Studies Department. This semester's Green Living Seminar is organized around the theme of environmental pollution. All presentations are free and open to the public. They take place on Thursdays at 5:30 here in the Feigenbaum Center for Science and Innovation, room 121. Today's presentation will last for about 45 minutes with an opportunity to ask questions at the end. And before I turn it over to tonight's speaker, I want to make a brief announcement about next week's presentation. Please come back and join us Thursday, February 20th, when Matt Reardon from the Massachusetts Department of Environmental Protection will be presenting a lecture titled Water Quality in the Hoosick River Watershed. Today's presentation, Road Salt, the Problem, the Solution, and How to Get There, will be given by Vicki Kelly, Environmental Monitoring Program Manager at the CARY Institute of Ecosystem Studies. Thanks very much for coming.
Thank you, Elena. Thanks for the invitation to come speak with you. Thank you to everybody who came out tonight on this cold and snowy February evening. It is really a privilege to be here to talk to you about this problem, this issue, and the work that I've been doing to bring attention to it and to start the conversation about how to address it, how to make changes. Okay, so here is an outline of my talk. I'll start with a little bit of a history of road salt use, how road salt was discovered in fresh water, how road salt behaves in the environment, and then I'll talk specifically about salt in our groundwater. I'll talk a little bit about the co-occurring issues, specifically the connection between road salt and lead in drinking water. And then I'll finish up talking about some of the best management practices to address the problem and the next steps that we need to take to make changes happen. So the history of road salt. The USGS, the United States Geological Survey, started reporting the use of road salt in 1940. At the time, they reported that the use in the United States was about 150,000 tons per year. There's some evidence that it was used prior to that. It's just that we don't have any reports of the amount and that it was being used. But we usually say that the onset of use of road salt on a wide scale was around 1940. In the 1970s, scientists started to discover and report salt in fresh waters. This is an abstract from a paper that was published in the journal Science. And for those of you who aren't familiar with scientific publications, the journal Science is a very prestigious journal. It covers everything from medical science to geology to physics to environmental science. So in order to get a paper published in this journal, the issue has to be very significant. So this was a paper published in 1971 in which they report that the presence of de-icing salt in Irondequoit Bay in Rochester, New York, and not only that it was there, but that they say during the winter of 1969 to 70, the quantity and salinity of the dense runoff that accumulated on the bottom of the bay was sufficient to prevent the complete vertical mixing of the bay during the spring. So not only was there road salt there, it was affecting the function of that body of water. This is another paper that was published the following year, again in the journal Science, and this time it's from East Central Massachusetts. And what they report is that they say the average steady state contamination of groundwater by road salt in the suburban area around Boston, they estimate will be around 160 milligrams per liter of sodium chloride. And that is if they continued to use salt at the rate that they were using it back then in the early 1970s. So let's put those numbers in a little bit of perspective. This is a little publication from 1975 in which these folks used concentration data from groundwater samples in the state of New Hampshire. And so in 1918 to 1924, they found that the concentrations of salt in the groundwater ranged from about 0.4 to 1.4 4.1 milligrams per liter. And that was 1918 to 1924. When they repeated this in 1968 to 1970, the concentrations had increased from a range of between 1 and 150 milligrams per liter. So by 1970, they were seeing elevated concentrations of salt in the groundwater in the state of New Hampshire. And when they tallied up the input of salt to the watersheds in that state, they discovered that, and they attribute those concentrations to primarily highway and town road de-icing salt. So what's happened since then? This is a graph that shows the amount of salt that has been used for de-icing in the United States in metric tons per year from 1975 through 2017. And what you can see, so each bar represents the total amount used in that year. And what you can see is a steady increase since 1975 in the amount of salt that has been used on the roads in the United States. Now remember that study, when I was talking about the history, in 1940 they reported the use of about 150,000 metric tons. And by 1975, it was up to around 10 million metric tons. And now, in the late 20-teens, we've doubled that. So it's now at about upwards of 20 million metric tons. So lots and lots of road salt entering the environment. So I'm going to show you a series of maps of the state of Connecticut. This is from a study that was published in 2013. In which they looked at the groundwater concentrations of salt across the state of Connecticut. And these were from samples collected as part of the Connecticut State Board of Health records. So this is a map of what the groundwater chloride concentration was in 1894. And the greener the map, the lower the concentration. So the dark green represents a range of about 2 to 2.5 milligrams per liter. And then as it gets yellower and then orange and red, the red represents concentrations of 250 milligrams per liter or more. So there we are, 1894, everything looks pretty clean. 1902, pretty similar, very low concentrations of salt in the groundwater. By 1920 to 1938, we're starting to see increases throughout the portion of the state where they had data, and then some pockets of concentrations in the range of about 25 to 50 milligrams per liter. By 1950 to 1969, we start to see pockets of pretty high concentrations in the range of 75 to 150 milligrams per liter, and then an increase in the spatial area that has elevated concentrations in the range of 5 to 25 milligrams per liter. By 1977 to 78, the distribution of concentrations that are elevated is increased throughout the state. Again, there's still a handful of pockets of pretty high concentrations. And then we get to 1992 to 2005. That you can see the state is looking a little less green and more yellowish green and yellow. So throughout the state, the concentrations are higher, and still there's some pockets. And here we are by 2007. It's pretty widely distributed. High concentrations are pretty widely distributed, with some fairly big areas with very high concentrations, all in the groundwater. And groundwater is where a lot of us get our drinking water. So, how did I get started doing this? I run a program at the CARY Institute of Ecosystem Studies in Millbrook, New York. It's out near Poughkeepsie. It's an environmental monitoring program, and part of the program involves collecting stream samples, which we've been doing since 1986, every month. And a few years ago, I plotted the sodium and chloride concentrations the average against time. And I discovered that we see, even in that stream, we see increasing concentrations. And this was somewhat confounding because the stream, the watershed that feeds the stream is mostly forested. And there hasn't been an increase in the number of roads or parking lots or houses in that watershed. So why do we see an increase salt concentration in that stream? Well, so we embarked on a study in which we tried to identify the sources of salt to the stream and try to figure out see if we could figure out why we see those increases. And so when we tallied up all of the different sources to the watershed feeding that stream, we discovered that over 90% of the salt that is in that stream comes from de-icing salt. It's from either road salt or parking area salt. There's a little bit that's from water softeners and sewage, not very much from natural sources or wet deposition. So that's striking. There's a lot of salt in the stream, and it's mostly from road salt. So this is a graph where we took that pie chart and we separated it into individual years. So each of these bars represents a year, and it's the total amount of salt that was put on the watershed from that source in that year. And so you see the sort of purplish color represents road salt. And when we did this, so because we have data from the stream, we know how much is moving out of the watershed through that stream. So we could do a little equation. We could say, we know how much is going into the stream. We know how much is moving out of the stream. So we do what we called an export minus input equation. So that sort of aqua colored bar, that's below zero in the very early part of the year and above zero in the later part of the study. That represents that export minus input. So if that number is negative, that means that there was more put down on the watershed than moved out through the watershed. And that means that the watershed retained that salt, probably in the groundwater. But there are other places that it could be retained. So what this graph tells us, when we plot this over time, we see that in the early part of the study, salt was being retained in the watershed. But then in the later part of the study, that number, that export minus input number, becomes positive. So that means that there's more moving out through the stream than was put down in that 1 year. And what this tells us is that the salt that's moving out through the stream in any 1 year includes salt that was put down years ago, decades ago. So this is really, really important. And this is why we see that increasing concentration in our stream. It's important because what this tells us is that there is a legacy effect of using salt. When you put it down today, it might not move out through the system for 20 to 30 years. Okay, so one of the things that we did was we wrote what's called a little model in which we said, we know all of the input, we know how much water there is, we know how much salt gets put down. We wanted to calculate what we would see, what we expected to see in the stream or in the groundwater in any one year. So what this graph shows is what we know, an increase in salt from about 1956 to the present. And then what we did was we ran this model out to predict what would happen if we extended out through time. And with this graph, what we did was we said, what if we decrease the amount of salt we use by about 18.5%? And that's what we calculate we can achieve using the methods that we have now to reduce the amount of salt that we use today. So this is what it looks like. If you run this model out over time, the salt concentration in the stream should go down, and it should reach what we call a steady state. It should level out. It takes a couple decades for it to reach that steady state. Just for fun, I ran the model with a reduction in road salt use to 0. Now, I'm not suggesting that we do that, but for illustration purposes, I ran the model with assuming that we stopped using salt altogether. And what you can see is that, in fact, if we stop using salt, the salt concentration in the stream and groundwater should go down to close to zero. But again, it'll take a couple of decades for it to get there. Again, I'm not suggesting that we do that. It was just for illustrative purposes. So one of the things you might notice is the black line represents what the actual stream concentration is. And you see that there is a lot of interannual variability. So there's years with really high concentrations and years with really low concentrations. And that is a little disturbing and interesting. We have in our stream some sensors. There's a sensor called a conductivity sensor. Conductivity is just the measure of the electrical conductance of the water. And the higher the concentration of particles of ions that have charges to them, the higher that conductivity is. So conductivity represents the concentration of salt. So when we plot the conductivity for a whole year, the average conductivity per day for a whole year, along with the level of the water, what we see, and on the x-axis here is what's called Julian day. That's just the day of the year. So Julian day 1 is January 1st. Julian day 365 is December 31st. The 270 is about late September. So what we see is, that you can see in the red graph, the conductivity is kind of high in the winter time, really spiky, and that represents the salt events. It goes down through the spring, and then it starts to rise through the summer. And as it rises, the water level goes down. And so when the water level goes down, the concentration goes up, and then it starts to reverse in the late fall. And so what this tells us is that water volume makes a difference. So the amount of water in the stream reflects the concentration of salt in the stream. And so what we think is happening in this graph, in this interannual variability, is that the years with really low concentrations are probably really wet years, especially in the summertime months. And the years with high concentrations were dry years. I'm going to talk a little bit about a project that we did in using data from a small township in New York called East Fishkill, in which we did a geographical analysis of the distribution of salt in groundwater. The data came from a public source. In this township, whenever a house changes hands, the well has to be sampled and analyzed and the data made public. So this provided us with a really a beautiful data set of about 1,000 points. They're drinking water wells throughout this whole township. And so in this study, we looked at some of the geographical variables and related them to that we found in these wells in this township. So what did we do? We asked a few questions. Overall, we were trying to identify, well, what are there geographical features that control where the salt is in the groundwater? And one of the obvious questions was, does the size of the road make a difference? Do the wells that are next to major roads have higher concentrations than wells that are next to minor roads? And what we discovered was that while we find higher concentrations in wells next to major roads, there's so much variability in the data that the difference isn't significant. And so in science, we always put data through a test, and a statistical test it's called, and we look for significance. That test tells us whether the differences we see are actually significant. So while we see some differences between major and minor roads, they're not statistically significant. And most scientists would say, well, then there isn't a difference. And this is different from what other studies have reported. Other studies have reported a significant difference between major and minor roads. What we did find to be important were two things. One, the distance to the nearest road. So the top graph shows on the x-axis the distance between a well and the road that's closest to it, and then the concentration in those wells on the y-axis. And you can see as the distance to the nearest road increases, the salt concentration decreases. So the farther away from a road your well is, the lower the concentration. And then the bottom graph shows the percent impervious surface cover, ISC. So when we drew a circle around each well with a radius of 250 meters, and we asked how much impervious surface cover is there in that circle, when we plotted that amount versus chloride concentration, we discovered that as the amount of impervious surface cover increases, the salt in the wells increases. And that makes total sense. Impervious surface cover includes roads and parking lots and sidewalks and roofs. So this makes sense. The more pavement, the higher the salt concentration. The analysis allowed us to do what we call the hot and cold spot analysis estimation. And so we asked the question, are there areas where the concentrations, high concentrations are clustered together or low concentrations are clustered together? And we did indeed find some hot spots and cold spots. There is a couple of spots that are sort of dark green, and those represent clusters of homes that have low concentration of salt. And then the red and pink areas represent places where the concentration, many of the homes had high concentrations of salt. We attribute it to a few factors, the one of which, and the one that's like in the center of the map, that's at a confluence of a few big roads. The pink one over to the left is an area that there's a road there that is heavily used and has a lot of sharp turns, and it's also in a low-lying area, so the water and the salt doesn't drain very well. And then up in the north, there's an area that is a densely populated spot. It is the roads that in that area are very narrow. It's very steep. The trucks that they have to use are the older trucks, the older, smaller trucks. So we think that explains the hot spot up there. So this analysis, we did find that there are clusters of areas that the salt concentration can be clustered in across the landscape. So how many of you are familiar or heard about the Flint, Michigan water crisis? A few people. Good. And so in that event, the lead that ended up in people's drinking water was, in part, it was leached out of existing pipes because the chloride concentration of the drinking water changed. It increased. They had been taking water from Lake Huron, and they switched to taking water from the Flint River, and they didn't add an anti-corrosive agent. And the chloride concentration from the Flint River was much higher than Lake Huron. So that raised everybody's eyebrows who's been working on this road salt issue, because it suggested that there might be a connection between salt, road salt, and lead in drinking water. This is a picture from the board game Clue. Has anybody ever played? Yeah. Oh, good. One of the weapons is a lead pipe. I don't know if anybody ever wondered what the heck a lead pipe is and why would you have something like that in a house? Well, there was a time when drinking water pipes were made out of lead because lead is flexible and they could bend it around corners, and lead gets hard as it ages. So that's why the lead pipe. No longer do houses have lead pipes, but there is lead in the solder that is used to stick pipes together. All right, so this is kind of a complicated picture, but I'm going to walk you through it. There are two ways that lead and other heavy metals can get into drinking water. One is through the leaching of soil, leaching lead through soil. and one is through pipes. So I'm going to talk about soil for a minute. And if you just focus on the picture on the left, on the top left is, this is a cross section. So these are both a cross section of the ground from the surface all the way down to where water is drawn for drinking water. So you see a house and you see a road at the top of the picture. And on the bottom left, there's a graph that illustrates the heavy metal concentration. So the darker the shade, the higher the concentration, the lighter the shade, the lower the concentration of heavy metals. And lead is a heavy metal. Okay, so when road salt is absent, you see that the heavy metals leach through the soil into the upper layer of the soil. They don't make it. So you see high concentrations in the upper layer and then really low concentrations in the lower layers where the well taps into. Now look at the picture on the right, and this is an illustration of when road salt is present. And then that little bar that has the letter A next to it, you see that the concentration of heavy metal is lower in that upper layer. And then if you look down around C, you see that the concentrations are higher. So when road salt is present, it allows those heavy metals to leach into deeper layers in the groundwater. So how does this happen? So this is a picture of a soil particle. The orange color is the soil particle, and a soil particle is like a magnet. It has all these negative charges around the outside surface. And floating in the water, the blue is the water around that soil particle. Floating in that water are ions. So sodium is an ion, chloride is an ion, calcium is an ion, and lead. And so they are all the positively charged ions stick like a magnet to that soil particle. And so you see a big green lead particle stuck on that soil particle. If you look to the right, the lead gets displaced. As you put sodium or calcium onto that soil particle, that lead is going to get displaced from the surface. And now that lead particle is in the solution. It's in the water. And it can go wherever the water goes. Down into the deeper groundwater in this case. So that's how that works. It's a mechanism called ion exchange. All right. So we have a mechanism. We have an idea of what's happening. Does it really happen? So this is a study that was published a long time ago, but a really elegant study in which they took tubes of soil. They took a bunch of tubes of soil and they put a mesh screen at the bottom of them. And then they poured water into them, of increasing. They had a tube and they poured deionized water into it. They had another tube of soil. They poured salty water into it, and they increased the concentration of salt. And then they caught what came out the bottom and they analyzed it for those heavy metals. And what they discovered, and you can see as you move to the right in each of these, the higher the concentration of salt, the higher the concentration of the metals that come out the bottom of the tube. So in fact, we do see that salt can cause the leaching of heavy metals from soil. So that's one way for heavy metals like lead to get into drinking water. What about lead pipes? So I'm going to talk a little bit about a study that was done in a little town called Orleans, New York, up on the St. Lawrence River. This was a study done by the same people who did the work in Flint, Michigan. And in this town, in Orleans, New York, there was a salt pile that was uncovered for many, many, many years. And the people in the town discovered that the concentration of salt in their drinking water was elevated, so much so that they couldn't drink the water. So they called me one day and said, look, we're worried about lead too. And I said, well, that, makes sense. I didn't have the capacity to do this work, so I put them in touch with these folks at Virginia Tech University, where, and they actually went up and made some measurements. And what these people did was they measured the lead concentration in the drinking water in the area down slope from where the salt storage barn was, and then throughout the township. So all the orange along those roads are places where they also sampled drinking water for lead. And what did they find? So the top two panels represent sodium and chloride concentration, and you can see that they were high next to the salt barn. The salt barn is that black dot in the map there. But if you look down to the bottom right, you see what they found in terms of lead. Pb is the symbol for lead. And what they found was that the lead was high in some areas, but not around where the salt barn was. So what this tells us is that there are some other confounding factors, like what is the lead content of the pipes in those homes that they sampled, and in the distribution system that leads to the homes that they sampled. It could be that there just isn't very much lead in the pipes near where the salt barn was, and we don't have that information. So the message from this was stay tuned. One of the things that they did in this paper was they created some pipe with some lead tin solder joints, and then they soaked it in water that had with increasing concentrations of salt. And then they analyzed that water for lead. And what they found was, as you increase the concentration of salt, you see higher concentrations of lead leached from those pipes. So this is suggestive that we need to worry about this interaction between salt in our water and lead that can be leached from the pipes in our drinking water system. All right, so hopefully I have provided you with enough evidence to convince you that road salt is a problem. It is something that we need to address, and we need to make some changes. So I produced a report the beginning of last year with the same title as this talk, Road Salt, the Problem, the Solution, and How to Get There. I have some copies of the report with me tonight. If you'd like one, come see me afterwards and I'll give you one. It's freely available online. And in this report, we make some recommendations about how to address this issue. And there are some low-hanging fruit, one of which is the salt storage facilities. Clearly, we need to cover our salt piles, and we need to cover them well. So they need to be completely covered. The salt needs to be completely underneath those roofs, and the roofs need to be made out of something that doesn't leak. So that is a no-brainer, if you ask me. There are some best management practices that are being implemented at various levels around the country. There are computer controls that you can put on trucks. You can install them on even the older trucks, and that allows the driver to slow down the hopper that is distributing the salt, or to even shut it off. So when they're stopped at a stoplight, they can shut their hopper right down. There are some that are sophisticated enough that they automatically do that. They measure the speed, sometimes the incline of a moving vehicle, and adjust the distribution of salt based on that. There are plows that now have blades that conform to the surface of the road, and that allows those plows to remove the snow more completely. So less salt is needed. Pre-treating a road surface with brine can reduce the amount of salt that's needed by up to 40%. So that's a really, really big step. And then there are what we call road weather information systems. They're all over the place, and they do things like take measurements of the surface of the road, of the air, and sometimes there's even cameras, and they allow drivers to actually check in real time. Instead of running out there with their truck and treating a road, they can look and see if the road needs to be treated. So these are all systems that can be put in place to, and they allow for the reduction of the amount of salt that's used, while the roads are still maintained as in a safe manner. Protecting our drinking water. The U.S. Safe Drinking Water Act is designed to do just that. In the Safe Drinking Water Act, there are different levels of standards. There's primary levels, primary standards, such as for lead, and these are enforced standards. Your water, if you're drinking water from a public source, the concentration of lead and other primary standards, they can't go above a certain concentration. There are secondary standards, and chloride fits into this category. These are non-enforceable standards. They're just guidelines. And so the U.S. EPA, which administers the Safe Drinking Water Act, says that chloride shouldn't go over 250 milligrams per liter. And then there's a list. There's a list that's called the Contaminant Candidate List. And these are elements that are under review, and sodium fits into this. So it has been a candidate for probably about 30 years, and the EPA recommends, but doesn't enforce, that that drinking water shouldn't exceed 20 milligrams per liter. There are some states that are more stringent, and they actually require public utilities to notify their customers if the sodium concentration exceeds that number. So one of the recommendations we make is to consider shifting sodium from that review list, from the contaminant candidate list, and make it a primary standard so that drinking water is required to be within that 20 milligram per liter limit. It's important to note that the Safe Drinking Water Act covers only public drinking water supplies. It doesn't cover private drinking water. So if you get your water from a well, you're not covered by this act. So what about those private drinking water wells? Well, we discovered in that study in the township of East Fishkill, New York, that half the wells sampled had concentrations of sodium that exceeded that 20 milligrams per liter. So one of the things we recommend is that people who are using private wells for drinking water get their well water tested regularly, and to test it for not just sodium and chloride, but also lead and some of the other heavy metals. There are impediments to implementing these best management practices, and in this report we talk about this. For example, not a lot of communities have the money for the upfront cost of new equipment. And so there's opportunity to consolidate services. So maybe a township combines the efforts with a county or even the state to allow them to treat some of their roads with the newest equipment. Private contractors are a big black box. We have no idea what private contractors do because they don't have to report. The state of New Hampshire offers liability relief. So a private contractor is maybe taking care of a parking lot at a hospital or a mall or an apartment complex, and they have a disincentive to reduce the amount of salt they use, right? Their customers want to see a lot of salt on the ground. And they use a lot of salt because they don't want to be held liable for any injuries. So the state of New Hampshire said, look, we will offer you liability relief. You can't be sued if you attend and if you attend courses on best management practices and you implement some of those practices. Many companies and organizations have sustainability plans. You may not know this, but the Target, the store, has a sustainability plan. So we recommend that those companies and organizations include salt, the use of salt and the storage of salt in their sustainability plan. And again, salt storage, getting private contractors to store their salt completely covered, is again, to me, low-hanging fruit. The level of service, when a couple of communities out west surveyed their citizens, they discovered that in many places, the citizens are perfectly fine with their roads not being salted. You know, they live on a back road, they know how to drive on ice and snow, they don't drive fast, so they said, yeah, it's okay for us if you don't salt our roads. So we recommend surveying the public in some places. Find out how people feel about this. If you don't need to salt, then don't salt. And this would entail engaging the policymakers in this process. And then lastly, research. There's an organization called Clear Roads. They have a really nice website, clearroads.org, and they have been studying these best management practices and reporting on the effectiveness. So that's a good place to go to find out which ones work the best. We recommend that we need to build data collection into management plans. A lot of smaller municipalities and those private contractors don't keep track of how much salt that they use. And we need to amend that. We need to be able to get that information to know how what we're doing is working. So here are my takeaways for tonight. Balancing environmental stewardship with safety and fiscal responsibility is possible. Remember I talked about that legacy effect. What we put down today might not move out of the watershed or out through the streams for decades. So we need to start to act now. And in order to do these two things, we need to create a culture of change. We need to engage our fellow citizens in this discussion, and we need to start talking about changing how we use road salt. So I'll leave you with this quote from Margaret Mead. Never doubt that a small group of thoughtful, committed citizens can change the world. Thank you all for your attention. You've been great. I'm happy to take questions, and if you'd like a copy of that report, let me know. Any questions? Questions?
What are the drawbacks of using calcium chloride?
So calcium chloride is a liquid. So now you have all these trucks that are set up to take solid sodium chloride, rock salt, and distribute it. You have to switch out those trucks. So a lot of small municipalities don't have the capacity to do that. It is slippery. If it's too warm, so if you put calcium chloride down and the temperature goes up, you've created a worse problem. It's a little bit more expensive, and it's still chloride-based salt, and then now you have calcium that you're dumping into the system. So, yes.
What about extraction, absorption technologies to take some of the salts out of the water?
Yeah, so that's a really good question. Recently it's been discovered that there are catchments, these stormwater catchments that catch water after it runs off of a road before it gets to a stream. And so there's a bunch of work being done to try to catch the salt in those catch basins and then use like plants to sequester the salt out of the soil and then remove the plants. Again, that will remove a little bit. Really the best thing that we could do is to improve our efficiency. So if we use less salt, there's less salt going down. All of us, I'm sure everybody in this room has seen a spot on the road where there's just a big pile of salt that just got dumped and didn't get swept up. We see that all the time. So making changes to prevent that from happening, doing things so that we have to use less salt to get a road surface to be ice-free is what is really going to make a difference. Trying to sequester the salt after it's down into the environment is a really, really difficult. Not cost effective, but again, I think it's worth looking at and continuing to research. That organization Clear Roads reports on stuff like that. Way back in the back.
What's the economic difference between brining the road beforehand and not brining the road? Are you using two sets of workers and two different sets of trucks and now is brine, like we think of brine as a sugar salt solution?
It's just salt. So brine is just a really, really concentrated solution of salt. You take salt and you mix it with water till the salt won't dissolve anymore. So there's no sugar. There is an upfront cost. So you obviously need to have trucks that can distribute a liquid. But think about it. If you are able to reduce the total amount of salt that you need by 40%, you're now reducing your salt, the budget, the amount of money that you need to purchase salt by 40%. So a huge savings, both environmentally and fiscally. Yeah. Back there.
How efficient would it be to use alternatives like coffee grounds or ashes or things like that and using it as like incentives for recycling and community-based initiatives? Mm-hmm. I don't know if you know about the efficiency of using those.
I have not heard about coffee grounds. Do we drink that much coffee, really? That's pretty bad. My daughter today pointed out I drink too much coffee. But so I haven't heard about coffee grounds. There are places where they're using like cheese brine and pickle brine, the beet juice, the waste from producing sugar from beets. All of those are really good. They don't work like salt. Salt is really the best thing at de-icing the road surface. And what those are good for are, what is really good to do is to take those brines and to mix them with salt. And when you do that, you could reduce the amount of salt that you need by a lot. I don't know, it's not 40%, but you could reduce it a lot. What happens is, one of the best management practices is to pre-wet the salt, and if you pre-wet it with some of those solutions like pickle brine or cheese brine, what happens is that when you put dry salt down on a road, it scatters, it bounces, and when you drive over it, it bounces, and it goes to the side of the road where it does no good. When you pre-wet it with those brines, it sticks to the road better. So it's now stuck to the road, it's not bouncing off to the side. So that means you have to use less. Overall, you have to use less salt. So those are good additions. Yes?
I was wondering if you know of any studies that have been done around native plants along roadsides or trees and how they're affected?
Yeah, there's a lot of studies that have been done, especially early on through the 1970s and 80s, about the effect of salt on roadside plants, and it's devastating. It kills them.
Yeah, I've noticed in just recent years, and maybe also like noticing an increase in salt use around here, and then also seeing like specifically the native plants, like fringe gentian, not in places that I've seen them growing for a decade now, not coming back in recent years.
Yeah, there are very few plants that are tolerant of salt. So, and it's not just plants. There are amphibians that are negatively affected by the salt. When the salt gets into their breeding pools, it can kill them. Insects. There's Phragmites, reed grass, that'll tolerate salt. You see that increasing all over the place, and that's next to roads. And that's partly because we've made the water there brackish from all our salt use. Back there in the way back.
Do you monitor waterways in any areas that don't salt? For example, just going to Pier and Vermont, they don't salt. Do you monitor that as some type of control to see what's going on in those waterways? I
do not, but there are monitoring programs. I got a call from a woman whose her drinking water, the concentration of salt had gone way up, and she wanted to sue the town. And of course, I was like, I'm not touching that with a 10-foot pole. But I said to her, look, if you can convince your neighbors to stop salting, this would be a really interesting experiment. It would be a really, really good thing, piece of information to add to this puzzle. And I would be happy to, analyze her samples she of course didn't want to stop salting, but she did want to sue the town. Way in the way back.
My question was similar, actually, about sort of jurisdictional requirements.
Yeah.
Do the feds require so much salt on their federal highways versus state highways? And I was going to ask, kind of a similar thing about just since we're right on the Vermont line, anytime you drive up into Vermont, it seems like there's more snow, but they don't seem to put as much salt on the roads up there.
And people are able to drive. So the departments of transportation, especially the State Department of Transportation, is mandated by law in each state, and it varies by state, to maintain roads to a level of safety. And the language in that law is important. A lot of times it's pretty ambiguous, and so, in a court of law, what ends up happening is that they interpret it pretty conservatively. They use a lot of salt. So one of the things we recommend in our report is to look at that language, engage the policymakers, alter it, make it so that it's clear, and so that it gives the Department of Transportation clear guidelines and some ability to maintain some roads at a level that doesn't require them to use that much salt. So, looking at those state laws, especially the state laws, is really important. Yes.
So I did my first year of school at Franklin Pierce University, and it was on a lake. And they had dips for road runoff and stuff like that, but wouldn't that still affect the groundwater with the salt runoff and stuff like that?
That's a super good question. So one of the things that we're discovering when we look at these stormwater retention systems is that they catch that stormwater. So they're catching water that runs off of a road and preventing it from running into a stream. But that means that water is now sitting in that ditch or that retention pond, and it's leaching. So it's leaching down into the groundwater. And one of the things we're worried about is that that's going to increase the salt concentration in the groundwater. And maybe in some places it would be better to let that water run straight into the stream in the wintertime when the organisms are not active. So this is an area of study that's brand new. There's only been a couple of papers and a couple of studies that have looked at this, but it's something that we're really interested in and really following really carefully. Yeah. Yes.
I live right over the border in Vermont, and we use sand. Does that have you guys done anything about the sand and stuff like that?
Yeah, so a lot of places used sand for many, many, many years. And what happens when you use sand is that it now, as the rain in the spring comes, it'll run off into streams and then into lakes and reservoirs. And so that causes siltation. So that all that sand is going to sink to the bottom, and then build up so that now you have all this sand and silt in lakes. And so that's one of the reasons that we switched from using sand to salt. There are some places in Vermont, the Adirondacks, where they have switched back to using sand. The key is to sweep it up at the end of the year. So they have to send out sweeper trucks and shovel it all back into a hopper for the next year. So that we don't prevent that over-silting of streams, rivers, and lakes.
If we have one more question, we can do that before we want to invite people to come up independently.
What kind of guidance can you give a small municipality seeking to get technical assistance or grant funding to implement campaigns?
Are you from a small town, or do you represent no, that's a good question. I would look to that organization called Clear Roads. It's their goal to get the information and into the hands of everybody and to get everybody to be able to implement those. So that's the area, that's the place I would look first for opportunities to both combine, consolidate services with other communities, and look for grant funding for purchasing, and for what the best things to do. There are some things that small municipalities can do. I had a guy come up to me after a talk one time, and he said he was from a village, and he said his drivers, he was the superintendent, he said his drivers compete with each other. All he did was teach them how to calibrate their hoppers. So make sure that they know how much they're actually dumping down when they open the hopper. And his drivers competed with each other to use the least amount of salt and also get the fewest phone calls from irate customers. So there's a lot that they can do at no cost. That costs nothing.
So I'd like to suggest that anyone that still has a question that they'd like to ask our speaker to, please feel free to stick around. I think Vicky will stick around for a few minutes as well to come up individually. I'd like to thank Vicky once again so much for this presentation. Thank you for coming. Please come back next week. And if you aren't on my mailing list and want to get announcements about upcoming talks, please come to me and put your email address down. Thanks very much.
Thank you, everyone.